In this lecture, we'll see another approach towards regular languages using a simple model of computing called a finite state automaton. So first, once and for all, we fix A to be a finite alphabet. And we define a regular automaton, a finite state automaton or a finite automaton is a directed graph, and it's actually a multi-graph. You're allowed multiple edges between vertices. So let's say it's a directed multi-graph whose edges are labeled by the letters of the alphabet A. The elements of the set of vertices the elements of Q are called states of the finite state automaton. And there is a distinguished state Q0 called the initial state. Also, there is a subset, a class of states accepting states. So that's it. That's the definition of a finite automaton. Finiteness here refers to this Q being finite. And let me just begin by drawing an example of a finite state automaton. So we have Q0, an initial state, and then we have, let's say our language is 1, 2, 3, 4. So I'm allowed to label my edges by the numbers 1, 2, 3, 4. So if I'm at Q0, if I see 1, I go to the state Q1. And then I also allow loops here. So let's say if from Q1 I'll draw an edge like this, Q2, 2, and here I have two edges, one labeled 1 and one labeled 2. So it's a common convention to not draw multiple edges many times, but just write down their labels. And then I have Q3, 1, 2, 3, Q4. And this will be an accepting state. Usually an accepting state is just depicted by drawing two circles around it. Okay, so this is an accepting state. This is the initial state. There could be more than one accepting state. In this finite state automaton that I've drawn, there's only one accepting state. Okay. The automaton is said to be deterministic if for every state there is only one out edge with any given label. So for every A in A, there is at most one edge out of Q that is going out from Q labeled A. So this automaton here is deterministic. If I had put 1 comma 2 here, then there would be two edges going out of Q1 with label 2, namely this loop here going from Q1 to Q1 and this edge here going from Q1 to Q2. This automaton would no longer be deterministic. But here I don't have this, and this automaton, you can see from every node there is exactly one arrow with any given label. This is called a deterministic automaton. Now, the way automata work is that you feed them a word, and then depending on what state it is in, it will move to another state. So let's just give a definition. A word W is accepted by an automaton if there exists a path from Q0 to an accepting state, namely a state in the set QF, whose edges are labeled by A1, A2, AN, where W is of the form A1, A2, AN. These are the letters from the alphabet A, which form the word W. Okay, so how do you check if a word is accepted by an automaton or not? So what you do is start at Q0 and the initial state, and then what you do is at step I, if you are at state Q, then you have two options. If there is an out edge labeled AI going out of Q, so let's say it is Q and then AI goes to a state Q prime, then move to Q prime. So we'll say change state to Q prime. Otherwise, do not accept the word. Here we are assuming that W is A1, A2, AN. And after you finish reading the word at step N, after step N, if you are in an accepting state, accept W. Otherwise, reject W. Let me illustrate this with this automaton here and a word. So let's just copy this out. So here's our automaton, and let's take a word W. So the language here, the alphabet here is 1, 2, 3, 4. Let's take a word 1, 2, 1, 3, 2, 1, 4, 3. So what we do is we start at the state Q0, and there is a 1 at the first letter is 1, so we use this 1 to transition to the state Q1, and then there is a 2, so we use this 2 to transition to the state Q2, and then there is a 1, so we use that 1 to transition back to the state Q2 because there's an edge coming out from Q2 which goes back to Q2 and it's labeled 1. And then there is a 3, so we go to Q3. Then there is a 2, so we go like this. Then there is a 1, so again we go like this. And then there is a 4. Oops, there should be a 4 here. And then there is a 3, so we go like this. And at the end of this process, we are in an accepting state Q4. So this is accepted by this automaton. And in fact, you can see that there is a path from Q1 to Q4, namely the path 1, and then this edge 2, then this edge labeled 1, then this edge labeled 3, then this edge labeled 2, and then this edge labeled 1, 4, 3. There is a path from here to here whose edges are labeled by these letters of the alphabet. On the other hand, W equals 1, 2, 1, 2, 4 is rejected because you do 1 and then 2, 1 you end up here, and 4 there's no out edge from Q2 going to 4. So this is rejected, or rather let's say not accepted. And let's just look at one more example. What about W equals 1, 2, 1, 2? This is also not accepted because after you have finished this 1, 2, 1, 2, you 1, 2, 1, 2, you end up at state Q2, which is not an accepting state. So these two words are not accepted, whereas this is accepted. Okay. So now a language is called a-regular or automaton regular if it is accepted by a deterministic finite automaton. If it is exactly the set of words that are accepted by a given deterministic finite automaton. So this A here stands for automaton regular. An example of an A-regular language is RGWK is A-regular. That means the language of restricted growth words with largest element K is K-regular. In fact, the finite automaton is, this is an example, this is a finite automaton which accepts the language RGW4. To construct RGWK, you would just extend this to have states Q0, Q1 up to QK, and you can see here what pattern you should be looking for. And to see that this is indeed that language, recall from the previous lecture how we characterize the language RGWK. So remember that RGWK, W belongs to RGWK if all letters 1 to K appear in W, and secondly the first occurrence of I is before the first occurrence of I plus 1. And that is precisely what this finite state automaton checks. Once you have seen when you're at state Q0, you're just starting out, and the only letter that you're allowed at this stage is 1. And until you see a 2, you're not allowed to put any of the letters 3, 4, and so on. So you just keep looking for ones, and as long as you have ones, you stay in this state. Once you have a 2, now you're allowed to put in ones and twos. Once you have a 3, you're allowed to put in ones, twos, and threes. Once you have a 4, you're allowed to put in 1, 2, 3, and 4. And once you have that, you're already reached an accepting state, and you never go out for RGW4. So this automaton demonstrates, in fact, that RGWK is irregular. Now this so irregular languages, when we think of them as combinatorial classes, they have what are called recursive specifications. So to see this, let me just so given a finite state automaton, I'll just call it a finite automaton. Let Li be the language consisting of words W in W, such that, okay, so with states Q equals Q0 dot 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 Qk, let Li be W in W such that W takes the automaton to state I, to state Qi. In other words, just to be clear, this means that there is a path from Q0 to Qi with edges labeled. So here we take W to be A1, A2, AN, A1, A2, AN. Now this Li, how would you end up in state Qi? Well, you'd have to come from some other state Qj such that there is an edge joining Qj to Qi, which is labeled by A. So what I claim is that Li as a combinatorial class is the sum of over all letters A in the alphabet such that there is an edge joining Qj, going from Qj to Qi, labeled by A. So at the previous stage you would have been at Lj, and you've added one more letter to your word, and so this term here corresponds to words that words in Li that end with A. So given a word in Li, W is going to be W prime A for some unique A in A, and W prime, say this belongs to Lj, then that means that there is an edge going from Qj to Qi that is labeled by A. Of course, there's one exception. You could just be at the empty state. So you have delta, you could have the empty word and be at the initial state. So you'll have delta I 0. So if I is 0, that means the language corresponding to the initial state, then the empty word takes you, leaves you at the initial state. So you can get to the initial state by the empty word, but to get to any other state, you would have to come through some other state using a letter A of your alphabet. So we have this specification that Li is summation over all A in A such that there is an edge A labeled A from Qj to Qi, x times Lj plus delta I0 epsilon. Now let A be the matrix given by Aij is equal to number of A in A such that there is an edge from Qj to Qi labeled A. This number could be 0 or it could be non-zero. So it's just the number of A in A such that there is an edge from Qj to Qi labeled A. Then we can write this equation here star as in vector form. What we'll do is we'll form a vector of combinatorial classes. Let L be the vector of combinatorial classes L1, L2, Lk. We already have addition and multiplication of combinatorial classes, so we can turn this into matrix multiplication and multiplication of matrices by vectors and so on. Then what we have is this equation here is just saying that L is equal to x times firstly you have epsilon 0 0 0 plus x times a L. So this identity is equivalent to this identity. This is saying that L0 is epsilon and here. So maybe I should call this L0. We have to start with the state L1 up to Lk. Okay. We can rewrite this as I minus xa, where I just means the identity matrix times L is equal to epsilon 0 0 0. Now if we write the vector generating function, Lx equals L0x, L1x, Lkx, then we have Lx is equal to I minus x times A inverse times the generating function times the vector 1 0 0 0, which is after all the generating function of this vector of combinatorial classes. Therefore, the generating function for the language accepted by this automaton is just the sum of generating functions corresponding to the accepting states. So those states which are in accepting Lix. In particular, Lx is a rational function. Let me show you how to do this in an example. So suppose we take this automaton that we had earlier. What is the matrix A? So this is RGW4. The matrix A is we have the initial state, there are no arrows going into the initial state. So we have 0, 0, 0. So there are 5 states here. So I'll have a 5 by 5 matrix. Now let's come to the state Q1. There's one arrow labeled 1 going from Q0 to Q1. So we put a 1 here. And from Q1 to Q1 also there's one arrow. So we put a 1 here. Q2, from Q1 there's no arrow going to Q2, but from Q0 there's no arrow going to Q2, but from Q1 there's precisely one arrow going to Q2. And so we have, so let me just index these rows and columns here. So these are indexed Q0, Q1, Q2, Q3, Q4, Q5, and similarly the columns are indexed Q0, Q1, Q2, Q3, Q4, Q5. Okay. So now from Q0 there's no edge to Q2. From Q1 there's exactly one edge to Q2. From Q2 to Q2 there are two edges, one labeled 1 and one labeled 2. So here I put a 2, 0, 0. And there's no edge from Q0 to Q3. There's no edge from Q1 to Q3. From Q2 to Q3 there's 1. From Q3 to Q3 there are 3 labeled 1, 2 and 3 respectively. And similarly. So you see the pattern here. For RGWK you'll have this matrix with integers 0 to k along the diagonals and 1s just below the diagonals. And what we get is RGWK x is equal to so let's use some notation. E0 is the vector 1 0 0 0 0, that is the 0th coordinate vector with the 1 in the 0th coordinate, and E5 is, let's call it E4 is the vector with a 1 in the 5th coordinate. Yeah. Then we have RGKX is just E5 transpose I minus XA inverse E1. That is exactly what this equation here, these two equations here boil down to. Now let me just end this lecture by saying something about the equivalence of A-regular languages and S-regular languages. In fact, there's a general theorem. It's called the Kleene-Rabin-Scott Theorem. The following classes of languages are equivalent or the same. So the first is languages uniquely matched by a regular expression, which means that you have a regular expression, look at the language of all words that match it, and each of those words must match it in a unique manner. Uniquely matching a regular expression. Languages matching a regular expression, uniquely or non-uniquely. I'd call these S-regular. Then we have languages accepted by a deterministic finite automaton. And the fourth is languages accepted by a non-deterministic or a general finite automaton. Any finite automaton. since the main focus of this course is on counting, I will not prove this theorem. It's just I'm putting it up here for your general perspective on these things.